Alright everyone, that implicit and logarithmic differentiation that is in section 3.5. To start off, I actually want everyone to take a minute and using the skills that we learned about the chain rule from section 3.4, try and see if you can do this problem. So everyone take a minute or so, pause the video, and see if you can come up with the solution on your own. All right, so coming back to it, we want to find the derivative of y given that y is the natural log of f of x. Side note, f of x can be anything. It can be the square root of x, it can be sine of x, it can be natural log of x. Yep, natural log of a natural log, who'd have thought? But the point is we can differentiate this just using the chain rule. So if you remember how your chain rule works, we start off by figuring out what the inside and outside are. So this f of x is the inside function. Log of stuff is the outside function. So using that, we know the derivative dy dx is going to be equal to the derivative of the outside. So we know that if I have a function that's natural log of something, the derivative is 1 over the something multiplied by the derivative of the inside function. So if the inside function is f of x, then its derivative is f prime of x. So writing this in its simplest form, we would write it as f prime of x over f of x. And there we go. That's the derivative. So implicit differentiation is basically like what we just did. The only difference is instead of writing our inside function out as f of x, we see it written as y. So, basic example. Let's say that we have a function y, and that function is, well, it may not even be a function, it could just be a relation. But anyway, that relation y is not explicitly defined, meaning it's not in a y equals some function of x form, right? So with the example that I wrote there, we have an equation that relates x and y to each other, but we don't actually have y equals value. And in theory, I could actually rearrange this to solve for y, but when I do that, caveat would be that I'm going to end up with a plus and minus square root of something, and it's going to be kind of ugly. Instead, an alternative, and the thing is, there are going to be times where you have an equation like this that you're not able to algebraically rearrange to y equals form. And in that case, or in cases where it just works easier, we can use a technique called implicit differentiation. So it works similar to how in the warm-up we had that f of x. If I were to pretend that this y here is f of x, then it works pretty much the exact same way that the warm-up did. The only thing is I'm going to take the derivative of every term in the equation. So looking at the first term, we have 2x squared. Take the derivative of 2x squared with respect to x. We get 4x. Second term, we have to treat like it's a composite function because I have 7y squared, but I don't exactly know what y is. I just know that it's a function that involves x. So I would treat it like, chain rule where y is the inside function and negative 7 stuff squared is the outside function. So start with our derivative of the outside, we get negative 14 stuff multiplied by derivative of stuff. And the derivative of y is just dy dx. Again, we don't know what that is yet, but dy dx, chain rule. Then on the other side, when I differentiate 1, I get 0. So at this point, all I'm going to do is use a little bit of algebra to solve for dy dx. So if I add 14y dy dx to both sides, I end up getting 4x equals 14y dy dx. All right, then if I want to isolate dy dx, which I do because this is what I'm trying to solve for, I'm going to divide both sides by 14y. So I end up getting dy dx is equal to 4x over 14y. And because we like to have our answers in simplest terms, I'm going to reduce 4 over 14 to 2 over 7. So we get 2x over 7y, and that's the answer. Because in a question like this, all I'm looking for is dy dx. I don't have to actually know what y is, and it's perfectly okay that I get dy dx in terms of x and y. Caveat to that is, remember, derivatives are used to give us information about a function. Like, for example, describe the slope of a graph at a point, right? Write an equation for a tangent line, things of that nature. And as we'll see later, relate the rate of change of one thing to the rate of change of another. Right, so with that, the caveat is that if I do solve for dy dx in terms of x and y, I won't be able to write the equation of a tangent line unless I have values for both x and y, which usually isn't a problem, but yeah, just want everyone to be aware of that. So, other example. Let's say that I want to write the equation of the tangent line at the point, we'll say 5, 3. Given that x squared over 10 plus y squared over 6 is equal to 4. Okay, so that's the equation of an ellipse. And we want to write the equation of a tangent line, so a line that's tangent to the ellipse at the point that's given. So to start with, let's find dy dx, because remember, if I'm writing the equation for a tangent line, I need to know two things. I need to know a slope and I need to know a point. Well, I already know a point, so I need to go back and figure out what the slope is at that point. So remember, your slope is going to be the derivative, dy dx, evaluated at the point that we were given. So I need to find dy dx, and then once I know dy dx in terms of x and y, then I can substitute the values of the point to find my slope. So going back to what we just did in the last example, we'll start off by taking the derivative of every term in the equation. So I can see with the first term, it's just power rule. So I'm going to bring the 2 down. We get 2x to the power 1 now over 10. And same thing with this, but remember, this is a composite function where y is your inside. So inside is y, outside is stuff squared over 6. Derivative of stuff squared over 6 is 2 stuff over 6. And then we have to multiply by the derivative, dy dx. And on the other side of the equation, we're taking the derivative of 4. Derivative of any constant is 0. And now we do a little bit more algebra. I'm also going to skip a step and just rewrite my fractions in their simplified form. So 2x over 10 will become x over 5. I'm going to subtract the second term from both sides. 2 over 6 can be rewritten as 1 over 3, so y over 3 times dy dx. Then I'm going to divide both sides by negative y over 3. But remember, when you divide by a fraction, that's the same thing as multiplying by the reciprocal of that fraction. So I'll get that dy dx is equal to x over 5 times negative 3 over y, or negative 3x over 5y. Okay, and that fraction can't be reduced, so that is dy dx. Now getting back to the problem, we know that the slope is our derivative with 5 plugged in for x and 3 plugged in for y. So that's going to end up giving me negative 3 times 5, because x is 5. That's the x coordinate, it's the one that comes first. Divided by 5y, so 5 times 3. 3 is the y coordinate from the point that they gave me. That's the one that comes second. And then when I multiply this out, I just see 15 over 15, well, with a negative in front. So this is negative 1. So the slope of my tangent line is negative 1. Or the slope of the ellipse at that point is negative 1. Now to go on and write the equation for the tangent line, I can use my point slope form. So you remember your point slope form is y minus the y coordinate. The y coordinate in this case was 3, is equal to the slope, which we just calculated as negative 1, multiplied by x minus the x coordinate, and the x coordinate they gave us was 5. And that's the equation for the tangent line. However, because your homework is online, it's going to want you to write it in slope-intercept form. So to do that, I'm going to start by distributing my slope. Distribute the negative 1. I get negative x plus 5. Then I'm going to add 3 to both sides, and I get y is equal to negative x plus 8. And that is the final answer. So now we've taken a derivative using implicit differentiation. We have seen what it looks like to write the equation of a tangent line. Now let's move on to an example that's a little bit more ugly. So for this one, let's say that we want to find dy dx. And we're given that the quantity sine of pi x plus cosine of pi y all raised to the 4th power is equal to 64. And we want to find dy dx. So this one is a bit of a double whammy because it gives you a chain rule, and within the chain rule it gives you an implicit, which is like a chain rule inside a chain rule. Yeah, these can get gross. But here's the idea. This starting off, the entire left-hand side of the equation is one big term that is composite. So we have the inside function is sine of pi x plus cosine of pi y. All of that is the inside. The outside function is stuff to the 4th. So when I go to take the derivative, I'm going to start by differentiating stuff to the fourth. That's going to be 4 stuff to the third. And then we have to multiply by the derivative of the stuff. So the derivative of the stuff, we start just term by term. First term, we've got sine of pi x. Well, that itself is also composite. So we know that pi x is going to be the inside of that one, and sine of stuff is the outside. So sine of stuff has a derivative cosine of stuff, but we have to multiply by the derivative of the inside. So I know this will work out to pi cosine of stuff. And then when I go back to the second term, notice that that is also composite. So pi y is the inside, right? Cosine of stuff is the outside. So in a similar manner, we'll get that the derivative is negative sine of stuff, but we have to multiply by pi. That looks messy. But in addition to that, pi is not the only derivative, the only part of the derivative of that inside. That inside also had a y in it, which means that we also have to multiply by dy dx. Okay, so this is where we are with the derivative of the left-hand side. Lucky for us, the derivative of the right-hand side is just 0. Not 6, 0. That's a 0. Yeah. All right, and the reason that that's lucky is because if you look at it, we have one term with 2 factors on the left-hand side. All right, this guy, switch color here. This guy is a factor. This guy is a factor. Since this is what I'm trying to solve for, dy dx, I can actually just divide the other factor just at this point already by itself. Well, not even divide, just think of it this way. If I have a factored form of something and it's equal to 0, I can solve the equation by setting each factor equal to 0. So if I do 4 times sine of pi x plus cosine of pi y cubed equals 0. Sure, that could have solutions, but remember, we don't really care about x or y. We only care about dy dx. Since this is not going to give me any useful information, I don't need it. Not helpful. The other factor, though, does involve dy dx. So I'll get some useful information out of that one. So if I set that other factor, pi cosine of pi x minus pi sine of pi y dy dx equal to 0, then I'll be able to solve for dy dx. So I'm going to start by adding this second term to both sides. And I can divide both sides by pi sine of pi y. So we get dy dx is equal to pi cosine of pi x divided by pi sine of pi y, which will reduce because pi over pi, since pi is a factor in the top and the bottom, we'll leave behind just cosine of pi x over sine of pi y, which will be our answer. Now, side note, you might be thinking, well, couldn't I use a trig identity to write that as just a single term, cotangent of something? The answer to that is no. In this case, you can't, because if you notice, the sine and the cosine have different arguments, right? The cosine has an argument of pi x, and the sine has an argument of pi y, right? In order for us to use any kind of trig identity to simplify stuff, we have to have the same argument in every trig function. Otherwise, it doesn't work. So now that we've done an ugly version, let's move on to the other topic, logarithmic differentiation. So logarithmic differentiation is a technique that you can use to actually make taking derivatives a lot easier in certain cases, or even just possible in certain cases. But before I actually get into an example with logarithmic differentiation, I just want to review some properties of logarithms. So first property that I want to review is that if I have a log, and it could be log base 10 or ln, which is log base e, if I take the log of something times something, remember that can be written as natural log or log of the same base of the first factor plus the log same base of the second factor. That's one of our properties. Another property is that if I take the log, and again I could use any base, ln just means I'm using the base e, which is Euler's number, which has a value of about 2.718. If I take the log any base of x divided by y, something divided by something else, I can write that as the log same base of the numerator minus the log same base of the denominator. That's another log property. And last log property I want to talk about is if I take the log, and again it can be any base, of something that's raised to a power, right? I can write that as the power multiplied by log with the same base of that base. So natural log of x to the n can be written as n times the natural log of x. And that last one is a property that you use basically every time you do logarithmic differentiation. The other properties oftentimes are useful when we're trying to simplify, or really just knowing those properties is a way for us to kind of tell when logarithmic differentiation can be helpful to us. So I'm going to start with just the classic version that everyone sees the first time they learn logarithmic differentiation. So for this example, let's say that we have a function y equals x to the power x. And we want to find the derivative y prime, also known as dy dx. First off, there are no derivative rules that we've learned so far that could differentiate this. It doesn't qualify as a power function because the power involves the variable. We can't use our rules for exponential functions because although the exponent does involve the variable, the base also involves the variable. So I can't use either of those rules. Instead, I'm going to use logarithms and implicit differentiation to help me out. So I'm going to start by taking the natural log, or I could use any base of logarithm I want. I normally use natural log of both sides of the equation. And the reason that that's helpful is because of that log property that we talked about way back here, right? If I have the log of something that's raised to a power, I can rewrite the logarithm as the power times natural log of the rest. So the right-hand side of this equation, I can write as x times the natural log of x. And the right-hand side is still the same, natural log of y. And by the way, when you take Calculus 2 and you learn more about, what are they called? Indeterminate forms, right? This property will definitely come in handy. And we'll learn a little bit about it, but not for this type. All right, so now that I've rewritten this, I can use implicit differentiation to solve for y prime, or dy dx, however you want to write it. So I'm going to start by taking the derivative of every term in the equation. Left-hand side, I only have one term, natural log of y. We know the derivative of that is y prime over y, right? So remember that's composite, y is the inside function, natural log of stuff is the outside function, and we get that. Second one, when I take this derivative, I have to remember my product rule, right? Product rule because one of my factors involves x, the other factor also involves x. So remember our product rule, derivative of the first times the second, so that's 1 times natural log of x, plus the first times the derivative of the second. And if you remember, natural log of x has the derivative 1 over x. So I end up with natural log of x plus 1 equal to y prime over y. So if I want to solve for y prime, or the derivative of y, I just need to multiply both sides of the equation, or every term in the equation, by y. So on the left, that's going to leave me with just y prime. On the right, I'm going to have y multiplied by natural log of x plus 1, which would satisfy our answer from implicit differentiation, but sometimes, like actually in this case, we could get our answer completely in terms of x. The way we do that is we remember, well, all I have to do is replace the y with what I know y to be equal to. Here I know what y is, so if I see a y in my answer, I can replace it with the original. So if I do that, if I just replace y with x to the x, I get an answer that is completely in terms of x. So my derivative, y prime, or also known as dy dx, is equal to x to the x times the natural log of x plus 1. And there we go. We used logarithmic differentiation to get that answer. Now another case where this can be helpful to us is when we have things involving like square roots, quotients, all sorts of nasty looking things. Yeah. So let's say that I have the function y equals the square root of x squared minus 9 over x squared plus 9. And there's going to be a caveat here that x must be greater than 3 or equal to 3. Yeah, x is at least 3. And the reason we need that restriction is because you cannot take the square root of a negative. Yep, so that just ensures that our radicand is a positive value. All right, so anyway, if I want to take the derivative of this, yes, I could use just regular chain rule, but I'd have to rewrite my function as a power, and then within my chain rule, I would have a quotient rule. Yeah, that just seems kind of ugh. But if I know logarithmic differentiation, I can at least make that square part and actually that quotient part a lot easier to work with. So if I take the natural log of both sides, we get the natural log of y is equal to the natural log of, and I'm going to go ahead and write my square root as a power. So this is the natural log of that square root thing, which I'm going to write as x squared over 9, or x squared minus 9, divided by x squared plus 9, all to the power 1/2. And the reason that's helpful is because we have that log property. If I take the log of something to a power, I can rewrite that power as a coefficient. So now I just have 1/2 times the natural log of x squared minus 9 over x squared plus 9. Okay, and the next thing that'll be helpful to me is to actually rewrite that quotient, because remember we had another log property that we talked about way back up here, that if I take the log of something divided by something, I can write it as the log of the top minus the log of the bottom. So getting back to our problem, I could rewrite this piece right here as two natural logs that are separate from each other. Very important to put the brackets here. That way we remember that that coefficient applies to both logarithms. So now that we've rewritten it like that, taking the derivative should be a lot easier. So we'll start off derivative of that left-hand side. We're going to get y prime over y. On the right-hand side, the 1/2 coefficient we can still keep outside as a factor that we could distribute later. And then we just take the derivative of each of these. Remember though, these are composite functions, each of these logarithms. The quadratics are the inside functions, log of stuff is the outside for each of them. So when I go through and do my derivative, I end up getting derivative of my inside, 2x, divided by the inside, x squared minus 9. Then for the second one, derivative of the inside, that's 2x, divided by the original inside, x squared plus 9. And then if I were to distribute this 1/2 to each of these terms, right, I could just write this as x over x squared minus 9 minus, running out of room there, x over x squared plus 9. And at that point, all I have to do is multiply both sides by y, and I get y prime equal to, and rather than putting y there, I'm actually going to go back and replace it with this original. So we're going to have the square root of x squared minus 9 over x squared plus 9 multiplied by x squared minus 9, 2x over x squared minus 9 minus 2x over, whoops, no 2 either. So x over, yep, x squared plus 9. And there, I've already managed to get my answer completely in terms of x. So I was able to use logarithmic differentiation to make an expression that had quotients, square roots, all sorts of nasty stuff, just in terms of a couple of logarithms. Made it way easier. So to summarize, we talked about implicit differentiation, where you have to remember every time you see a y, it's an inside function. So taking the derivative, you have to multiply by dy dx, or you could write it as y prime if that looks cleaner to you. Yeah, and then you just use algebra to solve for dy dx. We also talked about logarithmic differentiation, which uses the properties of logarithms to simplify derivatives or make ones that were impossible before possible. And there we are. That's section 3.5. Have fun.